Hello everyone, and welcome to this presentation of the 3DV 2021 paper entitled DPFM, Deep Partial Functional Maps. My name is Sohaib, and this is joint work with Gautam Pai and Max Ovzhanikov from École Polytechnique in Paris. Our goal in this paper is given a pair of shapes, we aim to find a point-to-point correspondence between them. In particular, we consider the problem of non-rigid partial shape matching, where the shapes in question are allowed to undergo non-rigid deformations and also exhibit strong partiality, such as missing parts or having holes, due for example to acquisition errors. In this work, we consider both problems of partial to full and partial to partial matching. Prominent prior works in this domain, such as PFM and additional follow-up works, propose an axiomatic approach which extends the functional map paradigm to the partial setting. However, these methods are based on heavy manifold optimization that takes a lot of time and typically use handcrafted features such as the prominent shot descriptor that are known to be sensitive to discretization of the surface. Concurrently, learning-based approaches for shape matching, such as geometric functional maps and follow-up works, propose an efficient solution to the problem of shape matching that learn features directly from the input geometry. However, they are not designed to handle the partial setting. In this work, we propose the first learning-based method adapted for partial shape matching. Our contributions are the following. We present the first learning method to deal with partial non-rigid matching in both scenarios, partial to full and partial to partial, achieving state-of-the-art results in many applications. Our pipeline predicts both point-wise correspondences and the region of overlap between partial shapes, making it the first learning-based approach for partial to partial non-rigid matching. We finally introduce two new challenging datasets and demonstrate robustness to mesh discretization as well as bidirectional partiality. Our method is based on the functional map framework. Here, we summarize the functional map-based shape correspondence pipeline. Given a pair of shapes x and y, we start by computing their spectral decomposition of the Laplace-Beltrami operator. Concurrently, we also estimate and stack together correspondent descriptor functions for the pair of shapes. Then, we solve a linear system to estimate the functional map by optimizing for descriptor preservation and certain regularity conditions if applicable. Finally, we recover a point-to-point correspondence from the functional map. We now present our main pipeline. DPFM is a deep learning network that performs partial shape matching. It takes as input two shapes, either full or partial, represented by their XYZ coordinates, and outputs a functional map that is then converted to a point-to-point map. Our pipeline also outputs two predicted overlap regions, indicating if a point on one shape is likely to exist on the other or not. DPFM is composed of four blocks. Let's look at the architecture in more detail. The first block is the feature extractor. Its role is to produce meaningful descriptors that will be used downstream for spectral matching. This module should be robust to rigid and non-rigid deformations, to the surface sampling, and more importantly, to the challenges introduced by partiality. In our work, we use the recent diffusion net architecture that has been shown to be robust under shaped discretization changes. We applied it in a Siamese way to extract features from both shapes. However, this configuration produces features that encode the geometry of each shape independently, and hence have no information about the other shape, thereby making the overlap region detection impossible. In fact, we showed that even in the presence of a perfect features extractor, it is still necessary to let the features communicate in order to recover the optimal functional map, especially in the case of partial to partial shape matching. In addition, features on the non-overlapping region should be equal to 0. To remedy this, we propose a new refinement block based on the powerful attention mechanism, which allows the shapes to communicate and makes the features of one shape informed by the features on the other shape. Specifically, we construct a bipartite graph where every point on shape X is connected to all points on shape Y, and we associate to each node the point-wise features learned from the feature extractor. The representation of each point is iteratively updated using information from points in the other shape. For this, we use a graph neural network based on the message passing formulation. Concretely, the value of each node I is updated using a message from the neighboring edges. Following the transformer architecture, the message passing is implemented as a weighted average of the learned values, with the weights being the similarity between learned queries and keys. The effect of the refinement model on the features is illustrated in this figure, where the intensity of the features is visualized. It can be seen that before the refinement, the intensity is uniformly distributed. Meanwhile, after the refinement, the features on the missing region tend to zero, as suggested by our theoretical analysis, which proves that the two shapes are now aware of each other. The next block in DPFM is the regularized fmap module. It aims at predicting the functional map between shape x and y. The functional map is computed by first projecting the refined features of each shape into their respective Laplacian bases. We obtain two matrices, A and B. We then use these two coefficient matrices to solve for the optimal functional map in a closed form. The final block in DPFM is the overlap prediction module. It produces a per point probability indicating whether the point exists on the other shape or not. This is done by applying a simple pointwise MLP to the refined features, already informed of the other shape. To train DPFM, three losses are used. The first one is the spectral loss that forces the predicted functional map to be close to the ground truth one in the L2 norm sense. In addition, we use the point info NCE contrastive loss, as the ground truth functional map can fail to provide important high frequency information, especially in the case of holes. The bidirectional cross entropy loss is used to train the overlap predictor by just comparing the predicted overlap probability with the ground truth label. Finally, the total loss is just a linear combination of the previous three losses. Now, let's show some results. We tested our DPFM architecture on the classical Shrek 16 partial benchmark, both on cuts and holes. Our method achieves state-of-the-art results. The Shrek 16 partial benchmark provides a good test bed for partiality, but it's composed of meshes that have similar connectivity. However, since it is known that some methods overfit to the mesh connectivity, such as short descriptors used by axiomatic methods, we introduced pfarm, a new dataset with the objective of testing the robustness of partial shape matching methods to significantly vary in mesh connectivity and sampling. In addition, due to the lack of benchmarks on the task of partial-to-partial matching, we introduced a new dataset, CP2P, composed of both human and animal shapes. The overlap between the source and target shapes varies from 10% to 90% of the total area. Once again, our DPFM method achieves the best results on these two new benchmarks, outperforming competing methods with a big margin. Here we show some qualitative results on the Shrek 16 dataset with texture transfer using the predicted maps. On the pfarm benchmark, only our method produces visually plausible maps. Finally, on the partial-to-partial benchmark, not only our method produces the best maps, but it's the only one capable of predicting the overlap region accurately. In conclusion, in this paper, we introduced the first learning-based method for non-rigid partial-to-full and partial-to-partial shape matching, demonstrating state-of-the-art results on a range of benchmark datasets. In addition, we introduced two challenging partial benchmarks to further stimulate research in this direction. Please check our paper for more results, visualizations, and an elaborate discussion of our method. The source code and data for this paper are available on GitHub. Thank you.